How's it going, Accelerated Chemistry? This is Mr. Spurk, and this is your Chapter 17, Section 4 notes on calculating heats of reaction. So we're going to first start by talking about Hess's law. Hess's law of heat summation states that if you add two or more thermochemical equations to give a final equation, then you can also add the heats of reaction to give the final heat of reaction. Hess's law allows you to determine the heat of a reaction indirectly by using the known heats of reaction of two or more thermochemical equations. So we're going to look at the reaction of diamond to graphite. Although this enthalpy change for this reaction cannot be measured directly because it takes thousands of years, you can use Hess's law to find the enthalpy change for the conversion of diamond to graphite by using the following combustion reactions. So the combustion of carbon, so we have carbon plus O2 yields CO2, and that has a delta H of negative 393.5 kilojoules. So we know that that is an exothermic reaction. We also have the combustion of diamond, which is still carbon plus O2 yields CO2, but this delta H is negative 395.4 kilojoules. So what we can do is we can manipulate these equations to try to find the heat of reaction of diamond to graphite. So we start by looking at our goal equation. And this is our goal equation. This is what we're trying to get to. We know two of the equations. We know that carbon graphite plus O2 yields CO2. And the delta H of this reaction is negative 393.5 kilojoules. We also know that the combustion of diamond is the same equation, but has a delta H of negative 395.4 kilojoules. So what we can do is we can manipulate these equations, add them together, and get the overall delta H for the reaction. So basically, we want to add these two equations together to look like our goal equation. So if you noticed, the graphite is a product in our goal equation. So what we can do is we can flip or reverse our top equation. So let's pick a different color here, and let's say now our first equation is CO2 yields carbon graphite plus O2. Now, since we inverted our equation, we need to multiply our delta H by negative 1. Sorry, that should be 393.5 kilojoules. So we had to, since we inverted our equation, we have to multiply our delta H by negative 1. And we can leave our bottom equation alone because we have diamond on the left-hand side. So we don't have to do anything here. And we don't have to change our delta H at all. So 395.4 kilojoules. So I'm just going to draw a line through here so we can kind of separate the two. And so what we are doing now is we're going to add up our equations. So let's go to orange, and we're going to add these two equations. If we add these two equations and cross off our spectator ions, we can kind of split these by reactants and products. And if something is repeated, we can cross it off, just like with our spectator ions. So in the top equation, we have carbon dioxide as a reactant, and in our second equation, we have carbon dioxide as a product. So we can cross off CO2. We can do the same thing with O2 because in our top equation we have O2 as a product, and in our second equation we have O2 as a reactant. So we can get rid of those two. So we are left with a final equation when we add these two together of carbon in the diamond form yields carbon in the graphite form, which is what we were trying to do. That's our goal equation. That's what we're looking to get. But now we just need to multiply together that -1 and the -393.5. So that just makes that number positive, and we add these two values together. We add together this value and this value, and when we do that, we get a delta H of -1.9 kilojoules. So we used Hess's law to find the enthalpy change for this conversion. So what we did was we took diamond to graphite, and we determined that the enthalpy change was -1.9 kilojoules. So I know that seems like a lot of writing. The slide looks very atrocious. It looks very messy. But if you follow through procedurally, it should make some sense. You're just going to manipulate your equations. So if you invert an equation, you have to multiply the delta H by -1. And we will definitely be talking more about this tomorrow in class. So for this reaction, we can compare their enthalpy changes. So we went from diamond to graphite, and that gave off -1.9 kilojoules. So it requires, or it gives off -1.9 kilojoules of heat to transform from diamond to graphite. So scientists weren't able to directly measure this, but through the two different combustion reactions, we were able to determine the heat of reaction. So Hess's law is useful when we cannot safely carry out a lab experiment, but when we need to determine the enthalpy of the reaction, much like we had to do with the diamond to the graphite. So what we can do with this equation is we can look at the combustion of graphite, because we know the delta H for that reaction is -393.5 kilojoules, and we know, or we're given another equation, that carbon dioxide gas can be decomposed into carbon monoxide gas and O2, and that delta H is 283.0 kilojoules. So what we can do is we can use these two known equations to solve for the delta H of our desired, or our goal equation. So it's sort of like a puzzle. We're piecing things together to try to find an unknown. We can also use this third equation that will help us cancel everything out. These are the three equations that we're going to need to use to determine the enthalpy change for graphite, for the combustion of graphite to the conversion of carbon monoxide. So now we're going to talk about standard heats of formation. Enthalpy changes generally depend on the condition of the process. STP is commonly used, and the standard heat of formation, or delta H subscript F, with a superscript like 0 or like a degree sign, but what that means is standard, of a compound. So the standard heat of formation of a compound is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. The delta HF of a free element in its standard state is arbitrarily set at 0. So what that means is if we had like O2 by itself, its standard heat of formation would be 0. Like I just said, for diatomic elements, they're going to be 0. So for a reaction that occurs at standard conditions, you can calculate the heat of reaction by using standard heats of formation. The standard heat of a reaction is the difference between the standard heats of formation of all the reactants and the products. So the standard heat of formation equals the standard heat of formation of the products minus the standard heat of formation of the reactants. So let's go ahead and do a quick problem with this. So what's the standard heat of reaction for the reaction of carbon monoxide with O2 to form CO2? So the first thing we want to do is write our balanced equation. So we are taking carbon monoxide gas, we're combusting it to get CO2. And we need to balance our equation. We can balance this equation by placing a 2 in front of carbon monoxide and a 2 in front of carbon dioxide. And so now we just need to determine the standard heats of formation for our products and the standard heats of formation for our reactants. So what we do is delta HF equals, remember it's products minus reactants. So our product is carbon dioxide and we have 2 moles of that. So 2 moles of CO2 times its standard heat of formation, and that is given to us as negative 393.5 kilojoules per mole. And that's all of our products, so we can bracket that one off. So products minus reactants. So our first reactant is carbon monoxide, so 2 moles of CO times the standard heat of formation of CO, which is negative 110.5 kilojoules per mole. And we add that, it's a terrible plus sign. We add that one's not much better, but we're going to go on with it. We add that to our other product, which is water, and we have 1 mole, or not, I'm sorry, not water, oxygen. We have 1 mole of O2 times its standard heat of formation, which is 0 kilojoules per mole. And then we can bracket that off. Sorry, that kind of got squished. So then what we do is we just add these together and then subtract products minus reactants. So delta HF, our products, when we multiply 2 times negative 393.5, we get negative 787.0 kilojoules. And we subtract that from our reactants. We add those two together, and we get negative 221.0 kilojoules. And then we're just going to subtract products minus reactants, and we get negative 566.0 kilojoules. So the standard heat of reaction for the reaction of carbon monoxide plus O2 to carbon dioxide is negative 566.0 kilojoules. And we know that that is an exothermic reaction. So if we look at the standard heats of formation are used to calculate the enthalpy change for the reaction of carbon monoxide and oxygen. The diagram shows the difference between the delta HF of the products and the standard heat of formation of the reactants, after taking into account the number of moles of each. So in review, Hess's law allows you to determine the heat of reaction indirectly by using the known heats of reaction of 2 or more thermochemical equations. For a reaction that occurs at standard conditions, you can calculate the heat of reaction by using standard heats of formation. The standard heat of formation equals the standard heat of formation of the products minus the standard heat of formation of the reactants. And that's it. I know this section was kind of a beast, but don't worry, we'll get lots of practice with it. This is kind of like a puzzle. So as always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.